Let's talk about aqueous solutions. We've seen how we can have solid, liquid, or gas as a state, but we've also mentioned aqueous solutions. And in aqueous solutions, we have a mixture of chemicals dissolved in water, and this helps the reaction become faster. And when we dissolve ionic compounds in water, it breaks up in its constituent cations and anions. And when we have polyatomic ions, the polyatomic group stays together as one ion with its own charge. Some compounds are soluble in water, like sodium chloride, which is salt. Others are not, like silver chloride. And we know that ions are present because the solution that is disassociated into its charged cation and anion will conduct electricity, because electricity is a measure of freely moving charged particles. And we know that some things, like we said, are soluble and others are not. These are some solubility rules, and these compounds that are generally soluble in water. I don't expect you to memorize them. I will give you this on the exam, but I expect you to have a general idea on how to use this table at least. So we have compounds that are generally soluble in water, like these here. So whenever you see these are generally soluble in water, but there are some exceptions. For this here, there are no exceptions. Anytime you see these ions, it's soluble. Okay, here for chlorine, bromine, and iodine, is generally soluble, but if it's hooked to one of these cations, then it's insoluble. And same thing with the sulfate ion, is generally soluble, but if it hooks up with one of these ions, these cations, it becomes insoluble. These compounds, on the other hand, are generally insoluble. They are generally solids. But again, we see that there's exceptions. So if you see hydroxide, it's generally insoluble in water, but if it hooks up with one of these cations, then it is soluble. Sulfur, same thing. It's generally insoluble, generally a solid. But if it's hooked up with one of these, then it becomes soluble. Same thing with carbonate and phosphate. Let's do a couple of examples to apply the rules that we learned in our solubility chart. Okay, for silver bromide, we look and we see the bromide, and the bromide is in our soluble chart. It's generally soluble unless it's hooked up with silver, mercury, or lead. And well, what do you know? It's actually hooked up with silver here, so that means it's insoluble. And we put an S for solid after that when we write our equation. Calcium chloride. Now, chloride is one of those that is soluble. It's in our soluble chart. It's got some exceptions, but calcium is not one of them. So it's going to be soluble. And we will put an aqueous after that. Lead nitrate, lead 2 nitrate. Nitrate is a soluble one, and it has no exceptions, so that should be an easy one. Anytime you see a nitrate, it's soluble, no questions asked. Sulfate is also generally soluble, but it has exceptions. And lead is one of those exceptions, so it's insoluble. And since it's insoluble, it's solid, it does not dissolve in. Okay, go ahead and give this a try to practice using the tables, and then replay the video to see if you got the correct answer. Determine whether each compound is soluble or insoluble. Okay, we have copper sulfide, and our sulfur ion is in our insoluble table, so it's generally insoluble. It has some exceptions, but it's copper is not one of them. So this is going to be insoluble. And it's going to be in the solid state. Sulfate is generally soluble, but it has some exceptions. However, iron is not one of those exceptions, so it's going to be soluble. Carbonate is in our insoluble chart, so it's generally insoluble. It has some exceptions, but lead is not one of them, so this is going to be insoluble. Ammonium chloride. Ammonium here is in our soluble chart, and it has no exceptions. So it's like nitrate. If you see nitrate, ammonium, acetate, lithium, it is in or soluble. Now let us apply the solubility rules that we've learned by learning how to write equations for precipitation reactions. And precipitation reactions are usually done by mixing aqueous solutions of electrolytes together. And when this is done, the reaction will take place from the cation and the anion exchanging in solution. And we usually end up with a compound that's insoluble in water. If we end up with a compound that's insoluble, it will precipitate out or come out as a solid. So suddenly we go from two aqueous solutions, and when we mix them together, we get a solid. Now, I've been giving you equations, chemical equations, in which I've been telling you the product. So let's learn how to predict the product as well from an ion exchange. So we'll follow these rules. First, we'll write the formula of the reactant and determine the ions present when the reactant dissociates, right? So we've talked about ionic compounds dissociating into their cation and anion. So here we have sodium carbonate, and when it dissociates in solution, it ends up being positive sodium, so that's our cation, and our carbonate, which is our anion, plus our copper 2 here with our chloride, right? And when we have an ion exchange, so we mix this in a solution, we get a swap. We get our cation here will go with our anion here, and our cation on our second compound will go with our first anion. So the outside ones combine and the inside ones combine. And so let's exchange these ions in step 2 and write them and write their formulas. So here we end up then with the sodium going with the chlorine, okay, and then we have the copper. Don't forget that you have to write the metal before the non-metal. So the copper, positive 2, will go with our carbonate, polyatomic ion. Okay, now we're going to go to step 3 and cross the charges and reduce. So we're going to rewrite our equation without the mess of charges with it. So this is already given to us. This is aqueous solution. And the copper chloride. And now we write this. Now this is really easy because this NaCl is positive 1, negative 1. So we just write it as NaCl. And here this is positive 2 and negative 2, so they cancel out. And we rewrite them as carbonate. All right. Now let us do the fourth step and balance the equation. We have 2 sodiums on the left, so we're going to put a coefficient of 2 on the right. We have 1 carbonate on the left, so that's balanced. We have 1 copper on the left and 1 copper on the right. And then we have 2 chlorines on the left and 2 chlorines on the right. So we just had to add a 2 there to make it balanced. Now, let's apply what we learned about solubility. Let us figure out what our new products will be. Are we going to get a precipitate or a solid or not? All right, so NaCl is going to be a aqueous solution because chlorine is generally soluble in water. There are some exceptions, but sodium is not one of them. Carbonate is generally insoluble in water. There is exceptions, but copper is not one of them. So this is going to be a solid right here. So this is your precipitate. You will see that come out if you mix a solution of sodium carbonate and copper chloride. The anions and cations will do an exchange, and then you'll end up with a solid precipitate of copper carbonate. Okay, let us do another example. Write an equation for the precipitation reaction that occurs, if any, when solutions of lithium nitrate and sodium sulfate are mixed. If no reaction occurs, write no reaction. Okay, so we have lithium with a positive 1 combined with nitrate, and that is an aqueous solution because nitrates are always soluble. And we have sodium, which has a positive 1, with sulfate, which has negative 2. So we're going to have to put a 2 down here to balance out the compound to make it neutral. And sulfates are generally soluble. They have exceptions, but sodium is not one of them, so it's going to be an aqueous solution. So you see we have 2 aqueous solutions, and we mix them together, and guess what? We're going to get a swap. We're going to have an exchange of ions. So our cation here is going to go with this anion, and our cation here is going to go with this anion. And so let's write that then, our new compounds. So we have now lithium, positive 1, with a sulfate, which has a negative 2. So we're going to have to put a 2 here to balance this out. And we have our sodium. Don't write nitrate first, write sodium, because you got to write metal, cation before anion, right? So we have sodium with a positive 1 and a nitrate with a negative. Okay, so we already did the balancing to make sure that we have a neutral compound in each time. This is positive 1 and this is negative 1, so that should be simple. Let's rewrite our equation so it doesn't have charges in it. So we have lithium nitrate, that is aqueous, plus our sodium sulfate, which is also aqueous, and we have lithium 2-sulfate, and we have sodium nitrate. Okay, let's balance the equation. We have 1 lithium on the left and 2 lithiums on the right, so we're going to go ahead and put a 2 here. We have now 2 nitrates on the left and only 1 nitrate on the right, so let's put a 2 here. Okay, and now we have 2 sodiums on the left, great, and 2 sodiums on the right. And we have 1 sulfate on the left and 1 sulfate on the right. So it's all balanced. The next step that we want to do is determine the solubility of the new products that we made. Are we going to get a precipitate or not? Are we going to get a reaction, in other words? If you get a precipitate, precipitate, you will get a reaction. If both solutions are aqueous, then there is no reactions. Then all you have is a bunch of cations and anions swimming in solution. They do not recombine to form new product. Okay, so sulfate is generally soluble. It has some exceptions, but lithium is not one of them. Lithium is actually soluble for everything, no exceptions. So this is going to be aqueous. And nitrates are soluble with no exceptions, so that's going to be aqueous. Well, guess what? Since both of these are aqueous, we have no reaction. We do not see a precipitate. Okay, go ahead and give this a try. Write the equation for the precipitation reaction that occurs, if any, when solution of lead 2 acetate and sodium sulfate are mixed. If no reaction occurs, write no reaction. Alright, so let's start with lead. And we have 2. Acetate has the formula C2H3O2, but it has a -1 charge. So that means I have to put parentheses and put a 2 here to balance that out. Okay? Then I have sodium sulfate. So I have sodium +1. Sulfate is -2. So that means I have to put a 2 here to balance that out. And both of these solutions are aqueous, as we will look them up on the solubility charts that we have. And let's figure out what new reactions. So we have 2 aqueous solutions. We mix them together. Are we going to get a precipitate or not? Are we going to get a reaction or not? We will have an exchange of ions. This cation is going to go with this anion. This cation is going to go with this anion. So let's write the outer one first. So outside goes with outside, inside goes with inside. And we have lead 2 combining with sulfate. And these are both +2 and -2, so they cancel out, so I don't have to add any subscripts. And then I have sodium combining with acetate, and that's a +1 and -1, so they cancel out as well. I don't have to add any subscripts. So now let's just clean this up and write it without charges. So we have lead C2H3O2, that's our acetate. It's an aqueous solution. And then we have sodium sulfate. It's also an aqueous solution. And it makes lead sulfate plus sodium acetate. All right. Now let's balance the equation. We have one lead on the left and one on the right. Great. We have there's supposed to be a 2 here. We have 2 acetates on the left, but we only have 1 on the right. So let's put a 2 here. We have 2 sodiums on the left, we have 2 on the right, and we have 1 sulfate on the left and 1 sulfate on the right. So good. All we had to do was add a 2. Now, let us determine whether our new products are soluble or not. We have our sulfate, and sulfate is generally soluble, but it has an exception, and lead is one of those exceptions. So this is going to be solid. And acetates are always aqueous, no matter what they combine with. So there's no exceptions to that. Okay, well, since we have a solid, that means we got a reaction. So great. There is actually a reaction here. And this is our final reaction that is balanced with all of our states written in parentheses afterwards.